Here I'm going to explain the Model and Infer Analysis conceptually. Before I talk about the process, I want to talk about the end product of this analysis, which looks like this. This figure is a kind of map, where things that are farther apart are less similar, and things that are closer together are more similar. The skeleton of this map is defined by these nodes, which come from NMF factors. Each of these dots is a sample that we use to make the map, and these colored groupings are clusterings of the samples. So why is this useful? Onto the map, you can project either the features or samples used to make the map. This means that if you have other data about the same features or samples, you can annotate the map with that data. So maps like this can help us extract and visualize patterns in our data in an unsupervised way. With these maps, we can reproduce published findings and make discoveries of our own that may one day make a difference in a patient's life. With that in mind, let's talk about how the Model and Infer analysis works. We'll start with a feature by sample matrix. In this video, I'll explain the analysis assuming that we're using a gene by cell line matrix of gene expression. However, the analysis differs in places depending on what kind of data you're using, so I'll note these differences in the description below. The first step is data preparation. When we plot all our data, we get a distribution like this. The x-axis is TPM, or transcript per million, and the y-axis is count. First, we clean up the data by removing any rows or columns that contain all zeros. Then we shift the data above 0 and take the log of the data, which gives us a distribution like this. By taking the log, we didn't just decrease the range, we decreased the relative distances between data points to avoid overemphasizing the extreme values. Next, we standardize the columns by taking each value in a column, subtracting it by the mean of the column, and dividing that by the standard deviation of the column. When we do this for each column, our data is converted from log TPM values to z-scores. Plotting all the data again looks like this, where the x-axis is standard deviations away from the mean. Why do we do this then? Standardize these samples is a valuable practice because it allows for the direct comparison between sample groups despite different sequencing or data preparation methods. So standardizing the samples used to make this map makes it possible for us to project new samples onto it later. At this point, we have a matrix with about 50,000 genes and about 1,000 cancer cell lines, where the values are no longer TPM, but z-scores. Our goal is to extract patterns from this data, but our matrix is so large that it's difficult to decompose or make sense of. So the next phase of the analysis is to select genes or features that will be most helpful to us in extracting patterns from this data. Note that with some data types, filtering out samples is advantageous, but not in our case. So first, let's talk conceptually about how we should select genes. Here I'll use the NMF4A gene, a transcription factor which plays a role in the development of the kidney, liver, and intestines, as an example. This is the distribution of the NMF4A gene expression across all of our cell lines. We can see that most cell lines express NMF4A less than other genes, but there is a distinct group of cell lines that express NMF4A more than most other genes. Interestingly, there aren't many cell lines in between. So what does this mean? This means that there's a particular context where high NMF4A expression is a good thing and probably helps cancer cell lines survive. If cell lines in this context have unique NMF4A expression, they must have other unique transcriptional patterns. For example, maybe they have particularly low expression of APC. Then if we highlight these unique transcriptional patterns, we should be able to extract this context and other contexts from our data. This is precisely our goal. These contexts are the naturally occurring patterns in our data that we're looking for. We call the method used to highlight unique transcriptional patterns feature selection by context, and here's how it works. Feature selection by context can be divided into 3 steps: fit the data, compute context, and select features based on context. So the first step is fit the data. we're going to fit the distribution of HNF4A with the skew-t probability density function, or PDF, which can be defined with 4 parameters: location, scale, degrees of freedom, and shape. And in case you were wondering, n is the number of samples in the distribution. Roughly, the location is where the distribution is centered. Scale is the fatness of the distribution. The degrees of freedom describes how quickly the tails of the distribution disappear. HNF4A has a lower degrees of freedom because its right tail disappears slowly. And finally, shape is a number that defines the direction and magnitude of the skew. HNF4A is right skewed, so its shape is a larger positive number. For reference, the normal distribution, which you can think of as the boring PDF or the most common PDF, has infinity degrees of freedom and a shape of 0. The skew-t PDF for HNF4A, defined by these 4 values, looks like this. We can see that the skew-t PDF is capturing its large right tail. Even though I'm only showing one gene here, let's assume we fit a skew-t PDF for each of our 50,000 genes. Now we're ready to move on to the next step: compute context. To compute context, we need to create a reference PDF. The purpose of the reference PDF is to answer the question, what would a boring distribution at this location and with this scale look like? Then we can ask, how is our actual distribution different from this reference distribution? And context is a quantification of that difference. So to create the reference PDF, we're going to flip the skew-t PDF about its center, and then maximize the flipped curve's degrees of freedom, giving us this purple reference PDF. Notice there's no purple line extending to the left of the center line. That's because we only care about the purple curve in places where the green curve has a larger value than the purple. Now we're going to begin to quantify the difference between the green PDF and the purple PDF. First, we're going to compute the Kullback-Leibler divergence, a measure of entropy between each point on the green PDF, which is P, and the purple PDF, which is Q, giving us a new probability distribution that looks like this. Now we're going to take the cumulative sum of this distribution from the center outward, where the final y value will be 1. Then we'll multiply this cumulative distribution by the Kullback-Leibler divergence between the green and purple PDFs, which is an integer. Now, the more different the purple and green curves are, the larger the KL divergence will be between them, and the larger this distribution will become. Finally, this is our context distribution. Let's go back to HNF4A and plot its context distribution. You may notice that there is a plus sign next to the context distribution label, and that's because this red curve represents positive context. Because HNF4A is right skewed, it only has positive context. Genes that are left skewed have negative context, which is the blue curve in this plot. The only difference between them is that negative context is to the left of the center and positive context is to the right. It is possible for a single feature or sample to have both positive and negative context. However, do you notice a problem here? If negative and positive context both have positive values, how are we going to distinguish between them? If I save the context scores for these genes as is, I'm not going to know whether they have positive context or negative context. To solve this problem, negative context scores are saved as negative numbers. Now imagine that we compute the context like we did here for each of our 50,000 genes, and we save the context scores in a gene by cell line matrix. Now we can move on to the last step, select features based on context. So what we want are genes with the most context. Then our task is simple. First, we separate positive and negative contexts, and then we take the sum of the context scores across all cell lines for each feature and rank the features according to their sum. For simplicity, we make all the negative context scores positive. Let's select genes with the most context that come after the turning point of each rank distribution, which leaves us with about 2,300 genes from positive context and the same number from negative context, for a total of about 5,600 genes. Our data matrix that we'll use for the analysis ahead will have only these genes. We call this our signal matrix. But we need to consider the fact that the first step of the analysis is a non-negative matrix factorization, and the problem is in the name, non-negative, because at this point, our negative context scores are negative numbers, which don't work for NMF. So we came up with this simple trick to fix this. To each gene name in the signal matrix, we add a plus or minus to indicate whether that row contains positive or negative context values, and we make the negative context scores positive. If a gene has both positive and negative context, there will be 2 rows, one for its positive context and one for its negative context. This concludes our data preparation, and finally, we're ready for the analysis ahead. Remember, our goal is to extract patterns from this data. A great way to do that is using non-negative matrix factorization, where a starting matrix called A is factorized into matrices W and H, which when multiplied together produce a matrix very similar to A. The W is a feature by factor matrix, and the H is a factor by sample matrix. Now the number of NMF factors, also called the rank or K, needs to be carefully chosen by the person making the map. When choosing the number of NMF factors to use, consider this. When you use a large number of factors, the patterns you find may not generalize to other datasets because they're reflecting nuances specific to the dataset you're using. Another consideration when choosing the number of factors is the stability of the decompositions. In other words, for a given number of factors, how often does a single sample end up being clustered into the same factor? This stability, or cophonetic correlation coefficient, is high when samples are consistently clustered into the same factors over a given number of permutations. In this plot, the green is the stability of the W, the purple line is the stability of the H, and the pink is their mean. In this case, 13 and 16 factors both look like good options, but we're looking for a simpler map, so we'll go with 13 factors. This means we're going to use the H and W matrices with 13 factors to make our map. So the first step of making the map is defining its skeleton. You may remember that the nodes of the map come from NMF factors. We want to create a powerful and flexible map, so we're going to use both the H and W matrices. First, we're going to compute the distance between the H factors and themselves, and the W factors and themselves, creating 2 matrices of factor distance. Now we're going to take the average of each corresponding distance to create a mean factor distance matrix. Translating these distances into 2-dimensional space gives us the skeleton of our map. Now that we have the map skeleton, we can plot either samples or features onto the map. To plot a sample, we use the amplitude or enrichment of each H matrix factor in the given sample to place it on the 2-dimensional space. This sample, for example, is significantly enriched in factor 0, but has low enrichment in other factors, which means it'll be plotted very close to node 0. And a gene is plotted in the same way, but using W factor enrichments. Let's use this technique to plot all of our samples on the map. At this point, it seems like our samples are separating well on the map, and in most cases, we can clearly see which node is pulling a given sample the most. However, for samples like this one, it's difficult to tell which factor it's most enriched in and which other samples it's most similar to. To give us insight into samples like this one, we're going to cluster all of our samples in the H matrix. Just like with NMF factors, it's up to the person making the map to choose the number of clusters that's best for their analysis. Because there are 13 nodes in our map, let's choose 13 clusters. Now let's color our samples on the map according to the 13 clusters. And look, the ambiguously placed sample is surprisingly grouped with the orange cluster, something we wouldn't have predicted before clustering the samples. And we can use the same process to plot our genes annotated by their clusterings on the map as well. Now that we have our map, it's time for the fun part, annotation. But you're probably thinking, did we manage to extract distinct contexts from our data? Well, remember our old friend HNF4A? One indication of success would be if we annotate the map with HNF4A expression. The cell lines with high HNF4A expression group together since it's likely that this group represents a distinct cellular context. And check it out. Most of the cell lines with high HNF4A expression are down here, around node 7. Fortunately, we also have CRISPR data for these cell lines. And when we annotate with cell line viability after HNF4A has been knocked out, we see that these cell lines struggle to survive, confirming our previous suspicion that cell lines in this context depend heavily on HNF4A expression for their survival. If we continue to annotate this map, we find other characteristics of this context, like high tiger protein expression, and a dependency on the beta-catenin gene, which gives us insight into how we might treat cancers in this context. Thanks for watching.